doing well. I hope everything's going very well with you. So what I want to do in this video is I will go over all the 20 questions that came in our second major exam, which covered chapters from 21 to 26. And the topics that we're going to cover in this exam are Coulomb's law, electric field, Gauss's law, electric potential and capacitance, and finally electric current and Ohm's law. So these are the general topics, but these have like subtopics that we're going to go into during the exam. And you will find all the questions posted in a comment down below under this video. And I will also be adding the figures, so everything you will need to solve the exam will be added to the comment or to the description. So let's keep going. All right, guys. So in our first question, the question says that we have an infinitely long cylinder or an infinitely long rod. So when it says an infinitely long rod, it means a cylinder, because a rod is basically a cylindrical shaped object. Okay, so we're given the radius of the rod, which is 4.5 times 10 to the negative 2 meters. So we're given the radius in centimeters, but we will multiply that by 10 to the negative 2 in order to convert our SI units. And okay, so we're given the radius and we're given the electric field at the surface of the rod. Okay, so these two are the only givens in the problem. So we're given the radius and the electric field at a distance 4.5 centimeters from the center of the rod. Okay, so the first thing to think about when we solve these problems is that when we have a cylinder, a charged cylinder, we can assume that the cylinder is basically a line of charge. A line that is at the center of the cylinder. This is true because of Gauss's law. Like we have derived the formula. This formula gives you the electric field away from a line of charge. So this formula was derived from Gauss's law. So this also holds true if you have a sphere. You can assume as though it's a point charge. But in our problem, we have a cylinder. Okay, so if we know the electric field and we know the radius is basically r. So r is the distance away from the line of charge. So the electric field is 1.6 times 10 to the 4 power. So this is the electric field. So according to the formula, we have the electric field is equal to 2 times k. So k here is 9 times 10 to the 9 times lambda. So lambda is the linear charge density. Linear charge density is basically charge in coulombs over the length in meters. So if we know the value of lambda, so we're trying to solve for lambda, and after we solve for lambda, we can find the volume charge density. So the question is asking about this value right here. And in order to reach the volume charge density, which is the charge over the area, over the volume, so linear charge density is charge over the length, and volume charge density is charge over the volume. So we can solve for lambda from our Gauss's law, derived equation. So r here is the distance between the center of the cylinder and the surface. So just plug these numbers into your calculator and you'll be getting that lambda is equal to 4 times 10 to the negative 8 coulombs per meter. So lambda is the linear charge density, as we have said. Like, so it's unit charge per 1 meter. So after we have this, we're just one step away from the solution or the answer. So what we're going to do is basically divide lambda by the area of the cross-sectional area of the rod. So once we do that, we basically get this expression right here. So if we divide lambda by A, you'll be getting Q over A times L. A is the cross-sectional area, and L is the length of the cylinder. So area times length is equal to the volume. Like for any symmetrical shape, if you have, for example, a cube, so if you multiply the area, the cross-sectional area times the length or the height of the cube, you'll be getting the volume of the cube. So in order to get the volume of the cylinder, we multiply the area, the cross-sectional area, times the length of the cylinder. And so this here is the volume. So all we need to do is basically divide lambda by the area, the cross-sectional area, and you'll be getting 6.3 times 10 to the negative 6. And that's going to be Coulomb per meter cubed. And that would be your answer. Okay guys, so question number 2 is a reasonably challenging question. So we're given a circuit, okay? So we're in the problem, we're given this circuit. And at first glance, it seems a rather complicated circuit. But the key thing to realize about this problem is, and if you realize this key thing, you'll basically solve the whole problem. Okay, so this is very complicated, like a lot of capacitors, and they're not in order. But we can rewrite this circuit to be like this. And once we get to this form, everything else would be easy. Okay, so the positive terminal of the battery here is connected to the positive terminal of this capacitor, and it's also connected to the positive terminal of this capacitor and this capacitor. So, if you realize that the positive terminal of these three capacitors are connected by the same wire to the positive terminal of the battery, and then if you also realize that the negative terminal is connected to the negative terminal of this capacitor, and this capacitor, actually no, not this one, okay, and this capacitor. So as we can see that all the negative terminals of these three, this one and this one and this one, all these three capacitors, are connected by the same wire to the negative terminal of the battery. Then what does this mean? It means that these couple are in parallel with the battery. So we have three couples basically. Okay, so this is the first couple of capacitor, this is the second couple, and this is the third couple. Okay, so realizing that these wires are connected in such a way that all the negative terminals are connected to the same wire and to the same negative terminal of the battery, and this goes true for all the positive terminals as well, you would realize that this circuit right here is basically the same thing on this circuit. Okay, so at this point, we know that we have three couples of capacitors that are connected in parallel with the battery. So if you have any couple of capacitors that are connected in parallel with the battery, then the voltage difference across the two capacitors, like this one and this one, will be the same as the voltage difference across the battery, which is given in the problem, and it's 12 volts. Okay, so this is the hardest part of the problem. Then the second step, we're given the energy stored in all of these capacitors, okay? So what does it mean to have the energy stored in all of the capacitors? It means that if we add all these capacitors and represent them by a single capacitor, like this positive, negative, and this is 12 volts. So this is the equivalent capacitor, okay? So if you add all these and represent them by one single capacitor, then the energy stored in that equivalent capacitor is going to be equal to 1.1 times 10 to the negative 4 joules. Okay, so let's go ahead and do that. So we know that all of these capacitors have common capacitance, like they all share the same exact capacitance, which is C, okay? That is said in the problem. Okay, so in order to add two capacitors in series, so I'm going to go ahead and erase this. because this is the confusing circuit that we're given in the problem. But we don't need it anymore because we already rewrote it by in a simpler sort of form. Okay. So yeah, we were saying that, yeah, so we're trying to add the two capacitors in series. So if you want to add two capacitors in series, then all you need to do, so the equivalent capacitor is going to be equal to 1 over the first capacitance plus 1 over the second capacitance. So that is going to be equal to 2 over C, sorry. So 2 over C is basically 1 over the equivalent capacitance. So the equivalent capacitance is going to be equal to C over 2. So these two are basically something like this. And this here has the capacitance of C over 2. So we have 3 couples. Each couple has a C over 2 capacitance. So C over 2 plus C over 2 plus C over 2 in order to add this, and this. So you're going to have 3C over 2. That is the equivalent capacitance. So this here, our very simplified version of the circuit, has the capacitor in this circuit is basically 3C over 2. Okay, so once we figure this out and we know the equivalent capacitance, we use this equation. This equation basically tells you the energy stored in any capacitor, okay? If you have the capacitance and you have the voltage, we can figure out the energy using this equation. So we're given in the problem that the energy, U, is equal to 1.1 times 10 to the negative 4 joules. So we go ahead and solve for C. Because we know what V is, it's 12, and we know what the energy is, which is this value. And 1/2 is basically a number, so this here is the unknown in this equation. So if you go ahead and solve for this, you're going to get the equivalent capacitance, which is this that capacitor in here. And yeah, so you just plug your numbers in, and you'll be getting the equivalent capacitance, which is equal to 1 times 10 to the negative 6. Okay, so we're halfway there, and so we have an equation that would be our final equation in this problem. The equation basically says that the capacitance is equal to the charge over the voltage. Okay, so we know the problem is asking for the Q, okay? It's asking for the charge on each capacitor. So we go ahead and solve for Q. So Q is basically the voltage times the capacitance. And we already know the capacitance of each capacitor. We already know the capacitance of each of these capacitors. And that is going to be equal to 3 over 2. So here we solve for the equivalent capacitance. So if we multiply this value, after we solve for it, by 2 over 3, you'll be getting this value. This here is basically the capacitance of each of these capacitors. So once we do that, we're going to get 1 times 10 to the negative 6. So 1 times 10 to the negative 6 is basically this value. So it's not equal to the equivalent capacitance, sorry. So C is the capacitance of each of these capacitors, each single capacitor on here. Okay, so once we know the capacitance, all we need to do is basically multiply the capacitance by the voltage, and we'll be getting the charge on all of these, or on each of these capacitors. Okay, so since we know that this C is basically equal to this C, and all of these C's are equal, and we know that the voltage across these two equal capacitors is 12. So we have a rule, like when we have two capacitors in series, then the rule says that the total voltage is equal to the sum of each voltage of these capacitors in series. And since that these two capacitors are equal in value, charge is going to be distributed equally to these two capacitors, and therefore they're going to have the same voltage. So the total voltage, which is 12, these two are connected in parallel with the battery, which means the voltage across these two is going to be the same as the battery. So we basically divide 12 by 2. 12 over 2 is equal to 6. So the voltage is going to be equally distributed over these two capacitors. Okay, so once we do that, once we divide 12 by 2, we can get the voltage on each of these capacitors. So this is 6, and you multiply it by C. We just solve for it, which is 1 times 10 to the negative 6. And you will be basically getting this answer. So this here is your answer. And it is equal to the charge stored on each of these capacitors. And that's the question. Alright guys, so question number 3 is basically a 1-minute question. It's very easy, given that you know your physics. If you know the physics of this question, it's going to be very easy and very quick. So the question says that we have a spherical conducting shell. And this shell has a charge of 12 microcoulombs. And we know that if any conducting shape, if we have a charged conducting shape, then the charge are going to accumulate on the surface. Like the charge is going to be in the outer surface of our shape. So after we charge this shell with 12 microcoulombs, positive 12 microcoulombs, we placed another charge in the center of the shell that is equal to negative 5 microcoulomb. So after we've done that, the question asks what happens to the charge on the center, on the outer surface of the shell and on the inner surface. Like this is the inner surface and this here is the outer surface. So we're asked to find the value of the charge on the outer and inner surface. So what's going to happen is basically once we place the 5 coulomb charge on here, microcoulombs, this is negative, okay? So it's negative 5 microcoulomb. This negative charge is going to attract some positive charges on here, equal in magnitude but opposite in sign. So the charge here is going to be equal to positive microcoulombs, because this here is going to repel the electrons, 5 coulombs of electrons away from the inner surface. So we're going to have an inner surface that is charged with 5 microcoulombs. So think of what's going to happen if we repel. So if we repel 5 microcoulombs of electrons to the outer surface. So this here is like a repulsion sort of force. So in the past, before we placed this charge, we had 12 microcoulombs. But once the electrons moved away from the inner surface to the outer surface, so we added negative 5 microcoulombs. Negative 5 plus positive 12, that's going to give you positive 7 microcoulombs. And that is how it looks like after we place the negative 5 microcoulombs. So we're going to have positive microcoulombs in the outer surface and positive microcoulombs in the inner surface. And that is your result. In question number 4, we're asked to find the resistance of a heater. So we have a heater that increases the temperature of 1.5 kilograms of water, increases the temperature from 10 Celsius degrees to 50 Celsius degrees, which means that it changes the temperature by 40 Celsius degrees in 10 minutes, okay? 10 minutes. So we multiply the minutes by 60 in order to get to convert minutes to seconds. So it takes 600 seconds for the heater to increase the temperature by 40 Celsius degrees, and the amount of substance that was heated is basically 1.5 kilograms of water. So, and we know also that the heater operates by 110 voltage. So the voltage of the heater is 110, okay? So now we need to find the resistance of this heater. So this is a pretty straightforward question, and the first step here is to figure out the power. So we have an equation that gives you the energy required to raise the temperature of anything. Like if you have some sort of material and you increase its temperature, so this here is change in temperature. If you increase the temperature of any material by, for example, 40, like say it's 40 Celsius degrees, then you just multiply the specific heat of that material, and in our case it's water, and the specific heat of water is basically 4,190 joules per kilogram Kelvin. You multiply the change in temperature by the specific heat of water, or any substance for that matter, times the amount or the mass of the material that we heated. So the mass here is given, the problem is 1.4, and the specific heat is also given. It's a well-known value, it's in your equation sheet. And the change in temperature is 40, okay? So if you multiply these three values, you're gonna get this amount, okay? This here is the energy required to raise the temperature of 1.5 kilograms of water by 40 Celsius degrees. Okay, so now we have the energy, but we don't want the energy. We want the power. Because if we know the power, we could divide the power by the voltage, which is given here in the problem, and we get the current. If we get the current, we could divide the voltage, which is here, by the current, and we get the resistance. And the resistance is the value we're looking for, or we're solving for in this problem. Okay, so once we figure out the energy, we must divide that by the time it takes the machine to exert this amount of energy. So this amount of energy is exerted each 600 seconds. So we divide this by 600 and we get this. So this value, or 419 watts, is basically the power that this machine or this heater generates per second. So we figured out the power. Now we just divide the power by the voltage, which is 110, which is a value that's given in the problem. And we're getting 3.8. So the current is basically 3.8. And now all you need to do is basically divide the voltage by the current, which is 110 by 3.8, and you'll be getting 28.9 ohms, and that is your resistance, which is the value that is asked in the problem. Question number 5, it's asking what is the value of this charge. So we have this sort of rectangle, and we have an unknown charge. Let's call it Q. The charge Q, the red one, it's unknown, and we're solving for this charge. So, and we have some sort of electric field in this surface. So the electric field is doing some work in order to translate this charge from point B to point A. So we know that the work is equal to the change in potential energy. So if we have like some sort of electric system, like charges Q1, Q2, and Q3, or Q capital, then if we want to do work on the system, like by an external sort of agent, then the work, or the applied work, is going to be equal to the change in potential energy. But if the system itself is doing work, like if these two charges are, for example, repelling and moving one of these charges away at some distance, then the work done by the system is going to be equal to negative the change in potential energy. But this here is not something we're interested in this problem. So we have some sort of electric field, and the electric field is doing work on the system in moving B from A, or in moving Q from point B to point A. So if you have defined work as the change in potential energy, and change in potential energy is basically potential energy final minus potential energy initial. So we have some sort of equation to calculate the potential energy, okay? The equation says that the potential energy is equal to the K. K is basically 9 times 10 to the 9th. It's a constant. And K times the Q1, or the first charge, times the second charge over the distance between these two charges. All right. So let's imagine the system in its final state. So first we're going to calculate this value, the potential energy in the final state. And then we're going to subtract from it the potential energy in the initial state. So we can get the change in potential energy. Okay, so in the final state, we're going to have Q1 or Q2 over here. And here is Q1. And we have already moved Q from point B to point A. And we have Q in between these two charges. Okay. So let's apply our equation over here. So K times Q capital, which is this, times Q2, which is here, times or over the distance between them. The distance between them is basically 0.05 meters. So this here is our first part of the potential energy. The second part is we take Q times Q1 as in here, and the value of this charge, multiplied by the value of this charge, divided by the distance between them, which is 0.05. So this here is something we have explained, we have just explained. And finally, the final part of our potential energy is basically Q1 times Q2 over the distance between them, which is 0.1. So the distance between Q1 and Q2 is basically 0.05 plus 0.05, and that is going to be equal to 0.1. Okay, so Q1 times Q2 over 0.1 and all multiplied by K. Because we have to apply the equation as it is. We cannot change anything in the equation. This here is the value of our final potential energy. So everything in here is known. K is a well-known constant, and Q1 and Q2 are known. So Q here is the only unknown in this sort of equation. And yeah, so we're basically trying to solve for Q, okay? So in order to solve for Q, we're going to calculate the initial potential energy. So the system initially was like this, okay? So Q was here. Before the electric field moved it from here to here. So the system is basically was something like this. Okay, so by the exact same logic, we apply this equation, and we have Q capital times Q1 multiply the two charges. In order to, one thing that I need to note over here is that when you multiply the charges, you take consideration of the sign. So here Q2 is negative, okay? So when you plug these values into your calculator, you have to plug in the negative sign as well, or you're not going to get the correct answer. So the distance Q2 times Q capital over the distance between them, this distance right here is basically square root of 2 over 20. How did we solve for it? Simply by using the Pythagorean theorem, which says that the hypotenuse is basically equal to the first side of the triangle, and this here, the other side is basically the same exact sum. So if we square this side plus the square of this side and take the square root of these two, add it together, you'll be getting the hypotenuse. C is the hypotenuse. So this here is the hypotenuse of a right angle triangle, and that's how we get the distance between them. So Q1 times Q2 over the distance, and we can apply the same logic for Q1 and the Q capital and Q1. And we also have this part which says that Q1 times Q2 over the distance between them times K is going to give you the potential energy or the part of the potential energy that is between these two charges. Okay, so once we have expressed the final and the initial potential energies, we can now subtract the initial from the final in order to get the change in potential energy, and which is equal to the work. Okay, so this here, actually, the red value is going to be subtracted from the above value over here. So this here is the same thing as here. So if we subtract, we basically multiply everything by -1. So this becomes minus, and this becomes minus. This also becomes minus. So the same exact value, same in magnitude, but always in sign, so it cancels. Then we sort of reduce our expression into something like this. So we took a Q capital as the common factor. So we have KQ times this big sort of expression. So I call this big. And we just solved this equation for Q. So Q is equal to the work, which is given in the problem, over K, which is the constant that we just talked about, times the big sort of value over here. So plug this number, these two, this here, into your calculator, and mind the signs. Do not ignore these signs, positive and negative signs. And you should be getting the value of Q capital, which is, I think, yeah, it's 2.42 times 10 to the -6. And don't forget to convert to SI units. So here we have it in nanocoulombs. So in order to turn it to coulombs, we multiply by 10 to the -9, okay? So basically just multiplying 10 to the -9 over here. Okay, so if you do this, you'll be getting this answer, which is the right answer. And that is the question. Alright guys, so question number 6 basically gives us some sort of capacitor. And so the separation between one terminal and the other terminal is 0.5 centimeters. And we have to convert that into meters by multiplying it by 10 to the -2. And if you want to convert centimeters to meters, you multiply by 10 to the -2. Okay, so what we've done is basically we inserted some sort of material or some sort of material that is going to increase the capacitance of this capacitor. So any material that we insert inside a capacitor in order to increase the capacitance, we call it dielectric. So we inserted some sort of dielectric over here. And we're asked to calculate the final capacitance of this whole capacitor. Okay, first thing first. First we need to know that the capacitance of any capacitor in the world can be calculated by multiplying epsilon naught times the area of the plate, okay? So if you have this sort of square plate, and so the area is basically this here. So this is some sort of side view. Here is the side view, and here is some sort of cross-sectional view. But anyways, this area over D. D is basically the distance between the two plates. Okay, so basically, if you multiply epsilon naught times the area over the distance, you get the capacitance, okay? So how can we use this information to calculate the capacitance of this new capacitor after we inserted the slab or the dielectric? Okay, so we could look at this capacitor as some sort of two capacitors connected in series. Okay, so the first capacitor is at this one. This over here. This is C1. And the other one with the slab in it, it's C2. So let's calculate C1 first. So C1 is basically, if you can apply the equation as it is, like you're gonna get epsilon naught times 0.5, which is the area over the distance. This distance, which is 0.2, times 10 to the negative 2, and you'll be getting some sort of value, okay? And if you want to calculate the other capacitance, which includes the dielectric, you just multiply the rule as before, like epsilon naught times the cross-sectional area over the distance. But this time, we have to multiply by 5, okay? So this here is some sort of a rule we have. It says if you have some sort of capacitance and we insert some sort of dielectric, then the new capacitance after the insertion is going to be equal to kappa times Q, times C. Kappa is basically the dielectric constant and it's given in the problem, which is 5. So that's why we multiply it by 5. So after you do that, you have to add these two capacitors as though these two capacitors are in series. So 1 over the equivalent capacitors or capacitance is equal to 1 over C1 plus 1 over C2. So C equivalent is going to be equal to the reciprocal of these two. And you just plug these numbers into your calculator and you'll be getting, I think, 2.4 times 10 to the negative 12, if I was not mistaken. No. It's not that. It's 1.7 times 10 to the negative 9. So that is equal to the equivalent capacitance after we insert this law. And that's your answer. Alright guys, so question number 7 is basically asking, so it says that we have some sort of charge, okay? And that charge is equal to 1.28 times 10 to the negative 16. It's a positive charge. And then we have some proton at infinity. So the distance, originally or initially, the distance between the proton and this charge is infinite. It's so long that it's equal to infinity. So the question says that we have fired this proton directly towards this charge. So we know that this charge is positive, and we know the proton is basically has a charge of positive E, the fundamental charge. The fundamental charge. The fundamental charge is basically equal to this, okay? 1.6 times 10 to the negative 19. So if you have a positive charge and another positive charge, and we know that if we take these two charges close to each other, that one of these charges are going to repel the other one, and the other one is going to repel the original charge. Because these two have positive signs or similar signs, they're going to repel. So if we fire the proton, it's going to have some sort of initial velocity, okay? The initial velocity will be constant at infinity, because at infinity there is no effect. The repulsion has no effect at infinity. But once it gets closer and closer, for example here, the electrostatic forces will start to act in this direction. And so if you have a force, then we have an acceleration in the same direction as the force. So it will decelerate the proton. So the proton will not be able to touch the other charge because of the electrostatic forces between them. So we will have some sort of deceleration, which is going to affect the initial velocity here until it becomes 0. Once the velocity becomes 0, this here, the proton will be constant or stationary. So when the proton becomes stationary, we have some sort of separation between them, R. It's called the separation R. So the question is asking, what is this separation? We want to figure this separation out. So this seems like a scary problem, but if you apply the laws of conservation of energy, which says that the kinetic energy initial plus the potential energy initial is equal to the kinetic energy final plus the potential energy final. This is basically saying that the energy initial is equal to the energy final. As long as there's no external forces acting in the system, then there shouldn't be any change in energy. Because as we know that energy cannot be created from nothing and cannot be lost, given that there is no external forces acting in the system. Okay, so the question explicitly says that at infinity we have no potential energy. So initial potential energy is out, cross this out. And we know that once the proton stops or becomes stationary, it does not move, so it does not have any velocity. And if an object does not have any velocity, then the kinetic energy will be zero. So kinetic energy final will be zero as well. So our equation reduces to this over here. Kinetic energy initial must be equal to the potential energy final. Okay, so this is easy to solve because we know the expressions for kinetic energy and potential energy. So kinetic energy is just basically 1/2 mv squared. The mass of the proton is in your equation sheets, and it's equal to 1.67 times 10 to the negative 27. And then the velocity, the initial velocity squared. This is the initial velocity. This value must be equal to the potential energy final, and the potential energy is just equal to K Q1 times Q2 over R. R is the distance between them, and it's the value we're looking for. Okay, so all of these over here in the numerator, all of these are values that we already know. So if you plug this equation into your calculator and solve for R, you'll be getting 3.8 times 10 to the negative 9, and that will be the separation between the proton and the charge after the proton is fired, and that is your answer. Alright guys, so for question number 8, it says we have a region with a uniform electric field. So uniform electric field that is equal to negative 5.60 times 10 to the power of 4. So it looks something like this. Because we have a negative and it's in the I direction. I means in the X. So if it says, instead of I, if it says in the J direction, then we're going to have something like this. Okay? So this is very important to understand. Okay, so, and we have a proton that is moving with a velocity, okay? So, okay, let's say that this is our proton. This proton is moving with a velocity in the positive x direction. Because we have a positive sign in here, and it's in the j direction. So, the velocity, so the proton is moving in that direction, in the positive x direction, and the electric field is negative. So if we have opposite signs, if you have an electric field with a sign that's opposite to the charge, then the electric field is going to exert a force on the charge opposite to the direction of its velocity, okay? The force exerted by the electric field on any charge in the electric field is equal to this equation. The force is expressed in this equation. So the force is equal to Q times the electric field. So the electric field is, here is the vector. So if the charge was negative, then the force would be in the opposite direction of the electric field. So the force would be in this direction if the charge is negative. But if the charge is positive, then our force is going to be in this direction, in the same direction as the electric field. So now we know that protons are positive. So if you have a charge that is positive, then the force exerted by the electric field on the charge is going to be in the same direction as the electric field. So we know that the force will be in this direction. So any force is going to generate some sort of acceleration. So we could express the force by this acceleration. So we know that the proton is moving with a velocity in the positive x direction, which is this. So if you have an acceleration that is opposite to the velocity, then the acceleration, what the acceleration is going to do is going to decrease the velocity until it stops the proton. Alright, so our job is to figure out how much distance the proton travels before it stops. And in order to do that, we're going to have to find what this acceleration is. We already know the velocity, okay? And we already know the value of the electric field, and we know the mass of the proton. But this here, the acceleration, is something we need to figure out. So we know that the force by the electric field is equal to the charge times the electric field. The charge of the electron is a well-known number, and it's equal to the fundamental charge, which is 1.6 times 10 to the negative 19. So if you multiply this by this charge by the electric field, you're going to get the force. Once you get the force, you divide the force by the mass of the proton, so you get the acceleration. So remember from 101, from physics 101, that the force is equal to the mass times the acceleration. So if you divide both sides by the mass, you're going to get force over mass is equal to the acceleration. So here, force over mass is equal to the acceleration. Okay, once we get the acceleration, we could use this kinematic equation for constant acceleration. So if the electric field is uniform, then we know the acceleration must be constant. So just solve for change in x. That's the value we're solving for, change in x, or how much the proton traveled. So we know that the final velocity will be 0, okay? Final velocity is 0. So just take the initial velocity to the other side with a negative sign and divide both sides by 2a, and you're going to get an expression for the change in distance. And plug these numbers into your calculators, and you'll be getting the answer, which is 1.35 meters, if I was not mistaken. Alright guys, so question number 9 is a conceptual question, and it says that if you have some sort of parallel plate setup, and we have some sort of electron that is released from very close to the negative plate, and it's released from rest. So we know that the negative plate is going to repel the electron, so the electron will have some sort of velocity in this direction. And it says that the velocity of the electron as it reaches the positive plate is equal to v, okay? So now, what if we decrease the distance between the two plates from d to d over 2? So they become closer. And then we do the same thing, like we release the electron from the negative plate, so the electron is going to have some sort of velocity. So we want to figure this velocity out. How does this velocity compare to this velocity? So, and the question also says that we do not change the potential difference. The potential difference between the two plates here is the same as the potential difference here. Okay, so we know from our equation sheet that the potential difference is equal to the change in potential energy over the charge. And we know from physics 101 that if the system is conserved, or there is no external forces acting in the system, then any change in potential energy must be corresponded with a change in kinetic energy in the opposite direction. If the potential energy goes up, this must be goes down, and vice versa. Like if the potential energy decreases, the kinetic energy increases. That's why we have a negative sign. So we could rewrite the potential energy as negative the change of kinetic energy. Okay, so and then multiply both sides. Now imagine that this here is not existing, and multiply both sides by Q naught. So you'll be getting Q naught times the potential difference is equal to the change in, here we have change, the change in kinetic energy. So we know that the initial velocity is 0, so this goes out. So our equation reduces to this. If you solve for the final velocity is the velocity here and the velocity here, you'll get this expression. So this here gives you the final velocity. And as we can see, that the final velocity depends on three things: the charge, and the potential difference, and the mass. The mass of the electron in both cases is the same, and the charge of the electron is the same as well. And the potential difference, as stated in the question, it will not change in both cases. Which means the final velocity here is the same as the final velocity here. Final velocity is equal to the final velocity. That is the correct answer. Of course, some of you might have picked some other choices because you thought that the electric field is the same. If the electric field is the same, then we're not going to have this situation. But here, the velocity here would be less if the electric field was the same. But if we do this sort of decrease in the separation and we hold the potential difference constant, this means that the electric field in this situation will be higher than the electric field in this situation, and that's going to accelerate the electron further, and we're going to have the same final velocity. And that's your answer. V in the initial situation is equal to the V in the final situation. Alright guys, so for question number 10, we have some sort of electric dipole, and we have some plates or charge plates, like positive and negative plates. So we have an electric field. We have two plates like this, and one plate is positive and the other is negative, then we have some sort of electric field. And it says that initially the electric dipole makes an angle with the electric field of 30 degrees. So then we have some sort of external agent that rotates the dipole like that until it makes, or until it's anti-parallel with the electric field. So anti-parallel means the electric field is like this, the dipole must be like this. And we know that both the electric field and the dipole are vector quantities. So one thing to note from the first measure is that if we have some sort of electric dipole, then the direction of the dipole will be going from the negative charge to the positive charge. So, so our vector will be heading like this to the positive side of the dipole. So if we rotate it from 30 to 50, we want to know the work required by an external agent to rotate the dipole to become anti-parallel to the field. And that's pretty straightforward. We know that the applied work is always, in any scenario, is equal to the change in potential energy. And we know, we have an equation in our equation sheet that says that potential energy is equal to the negative, potential energy of the dipole is equal to the negative, the value of the dipole dot the electric field, as in that dot product. Okay, so change in potential energy is basically U final minus U initial. So this here is U final, and this here is U initial. So minus with a minus becomes positive. So this here becomes positive. This is the initial potential energy. And here is the final potential energy. We know that by definition we need to have a minus sign. So if you want to kind of expand the dot product, then the expansion of any dot product is equal, for example, if we have, let's expand this here. And so we have we have the electric dipole dot the electric field. To expand the dot product, we have the value, the magnitude of the dipole multiplied by the magnitude of the electric field multiplied by cosine the angle between the electric field and the dipole. In this case, it's 30. And so on and so forth. And if you do multiply things out and add things out, you'll be getting something like 0.81 joules, if I was not mistaken. No. 87. Actually, it should be 0.187. Yeah, and that should be your answer. Alright guys, for problem number 11, we're given some sort of triangular shape, and we're given also that there's some sort of force horizontal to the horizontal with the x-axis, and it's heading towards the negative x direction. So we're given the sign and the magnitude of this charge, and we're given only the magnitude of this charge without any sign. And here we're asked to solve for this charge. Okay, so one thing that you need to understand is that the only way we could have a force horizontally on the x-axis headed toward the negative direction is by having this here to be negative, the charge here to be negative, and by the charge here to be positive. Any other choice of signs would result in something else. It will not result in a force horizontally aligned to the x-axis. Okay, let's try things out. Like, let's try all combinations. Let's say that you have negative and negative. If you have a negative and negative, and we already know this is positive from the question, then there will be a force pulling in this direction and a force pulling in this direction, and there will be a net force in the x-axis. And as we can see from the graph, the graph that is given in our graphs, there is no net force in the x-axis. Any combination that results in a net force in the x-axis is wrong, okay? So let's try another combination. So let's try positive and positive. If you have positive and positive, then we're gonna have a force in this direction and another force in this direction. And as a result, there will be some sort of force in a net force in the y direction, or in the y-axis. So this choice is also wrong. Okay, let's consider our last choice. The last choice is saying that this is positive and this is negative. What this means that we're going to have a force in this direction because these two are going to repel, and we're going to have a force in this direction because this and this is going to attract. So we're going to have a net force in the x-axis necessarily. Like if this was our choice, then we must have a net force in this direction. And as you can see, there is no net force in the positive x direction. We only have a net force in the negative x direction. So the only choice of signs that is left out is by choosing this to be negative and this to be positive. That way, we're going to have a force, a repulsion force from this charge, and an attraction force from this charge. And the y component of this force and the y component of this force are going to cancel each other out, and we're going to be left out with only the x component. So, as it says in the graph, we only have an x component in the x direction. So, according to this logic, this must be negative and this must be positive. Okay, with those out of the way, we can we can now go ahead and figure out the value of Q2. Okay, so from the graph, we can see that the y component of the force coming from 2, F of Q2, and the y component given from Q1 must cancel each other out. Otherwise, we're going to have some sort of angle, like this force, F here, will have some sort of angle, like this. But this is not the case. So, Fy from Q2 must be equal to Fy from Q1, okay? Or Fy from Q2 plus Fy from Q1 must be equal to 0. Okay, in order to kind of figure this out or solve for Q2, we first need to know the angles of the triangle. So if you have a triangle, a right angle triangle, and this is 3, and this is 4, and this is 5. We can use our inverse trigonometric functions to sort of evaluate the angles. If you know the sides of the triangle, then if you want to figure out, for example, this angle, let's call it theta. The value of theta will be sine inverse of the adjacent, which is 5, over the adjacent of theta is 4, over the hypotenuse of the triangle, which is 5. Sine inverse of 4 over 5 would be 36, and that is the value of theta, 36.8. And alpha is sine inverse of 3 over 5, which is equal to 53.13. Okay, so we know that this line over here is parallel to this line. So this angle must be equal to this angle. This is from middle school. And we know also that this line is parallel to this line. So alpha and alpha must be equal. Now that we have evaluated our angles, we can easily solve for Q2. Okay, so what we're going to do is we're basically going to apply Coulomb's law. Coulomb's law says that the force is equal to Q times Q1 times Q2 over the distance between them squared. Okay, this here is the same thing as here. It's Coulomb's law. It's the force between Q1 and Q2. Actually, Q1 and Q3. Okay? So, we take this force and multiply it by sine of theta. Why? Because if you do that, that is going to give us this component, the y component. And then add to that y component, the y component that's coming out of Q2, the force from Q2. So we do the same exact thing. Force from Coulomb is equal to K, Q2 times Q3 over the distance between them squared. And that is going to give you the force from Q2 on Q3. And if you want the y component of that force, then you have to multiply the force by sine of 53. So if you add the y component of the force coming from Q1 and the y component of the force coming from Q2, their sum must be equal to 0. Because our resultant force is only in the x axis, there is no y components in this force. Therefore, the sum of these two forces must be equal to 0. So now we have sort of derived the equation. Okay, so I just didn't want to confuse you guys. So once we have derived this equation, we could just plug this into our calculator and solve for Q2, and Q2 will be equal to 2.1 microcoulomb, and this is choice B, and yes, that's the right question. Once you get Q2, you have pretty much solved the question. Alright guys, for question number 12, it's a conceptual question, and it says that if we have some sort of battery, and the battery has some sort of voltage difference, and we have some sort of capacitor in here. Let's call it C1. And then we add another capacitor to the circuit, let's call it C2, and the capacitance of C2 is bigger than C1. So, and we're asked to compare the voltage difference across C1 before and after we add the second capacitor. We're also asked to compare the charge on C1 compared, before and after adding the second capacitor. So one thing we need to realize is that when we add two capacitors in series, then the total voltage, the voltage across the two capacitors, which is this voltage, the voltage is the battery, is going to be equal to the sum of the individual voltages on each capacitor. So if the total voltage here is going to be divided to the two capacitors, this means that each one of these capacitors is going to have a voltage that is less than the voltage on here. Because the voltage across this capacitor is also equal to the voltage of the battery. But here, the voltage on each of these capacitors is basically some other value less than this value, because the total voltage across these two capacitors must be equal to the voltage of the battery. So this means that the new voltage, will be less than the original voltage on C1. Okay, so now let's go to the charge. What's going to happen to the charge on C1 after we add the other capacitor? Okay, so we know that charge is basically V times C, the voltage times the capacitance. And we know that these two capacitors are in series, right? If we have capacitors in series, then the charge on each of these two capacitors must be equal. And also, the charge on these two capacitors must be equal to the charge on their equivalent capacitor. So, if we have two capacitors in series, the charge on each of these two capacitors are equal and is also equal to the equivalent charge on the equivalent capacitor. So by definition, the capacitance, when we add capacitance in series, then the equivalent capacitance must be less than any of the individual capacitances. As in, if you have any number of capacitors added in series, then if you add these capacitors, because they are in series, the equivalent capacitance must be equal to any of these individual capacitors. Okay? 1, 2, and 3. What does this mean? It means that the capacitance of the equivalent capacitor of these two is going to be less than C1 and is going to be less than C2. So this value will be small, okay? And we already know that the voltage is smaller than before. So because we're multiplying a smaller capacitance with a smaller voltage, then we're necessarily going to have a smaller charge. So our charge new must be less than charge original, and that is the solution for the question. Alright guys, for question number 14, it's a pretty straightforward question and it's just a plug-in question. But you have to understand the relationship between volume and area, or to be more specific, you have to understand the relationship between volume and Okay, so we're given in the problem the mass of the wire. So we have a wire, a cylindrical sort of wire, and we know the mass and we know the resistance of the wire. And once we're given the resistance, you have to automatically realize that resistance is basically resistivity times the length over the area. So resistance is resistivity times the length of the wire over the area of the wire, the cross-sectional area, like this area. Okay, so we have the mass, we have the resistance. Are we given the mass density? The mass density is mass per unit volume, which is kilogram per meter cubed. And we're also given the resistivity. The resistivity is this value, which is 1.7 times 10 to the negative 8. So, and we're asked to solve for the length of the wire. Okay, so the first thing we need to do in order to solve this question is figure out the volume. And why do we need to figure out the volume? Because the volume is basically area times the length. And if we rewrite the volume as the area times the length, we could rewrite this equation into one variable. Like, we could have this here as given and this given, and reduce these two variables into only one variable, and then solve for that variable, which is the length. So in order to get the volume, we're basically going to divide the mass by the density. Because density is basically mass over volume. So if you divide the mass by the density, you get the volume. Okay, the next step is realizing that the volume is basically the cross-sectional area times the length. This here is the area, and this here is the length. So if you divide both sides by the length, the area is going to be equal to volume over the length. Which means that the resistance is equal to the resistivity times the length over the area is going to be rewritten as the volume over the length. So resistance 0.5 given in the problem, resistivity given in the problem, times the length, the volume we're solving for, over the volume over the length, which is the area. So now we have this equation with only one variable, and we could solve for that variable, and we get 1.8 meters, and that would be your answer. All right, guys. For question number 15, it's a pretty easy question. Like I would say, it's only 45 seconds. This question. It's basically a gift in a reasonably challenging exam. So we're given the potential as a function of x and y. So this is a function of x and y that gives you the potential. And we already know from our equation sheet that the electric field is basically the partial derivative of the potential. So the electric field in the x direction would be the partial derivative of the potential with respect to x. So if you differentiate this whole equation with respect to x, you deal with y as a constant, okay? So here, 5xy differentiated with respect to x, if you consider y and 5 as constants, then the derivative of this here is equal to 5y. And the derivative of 12x squared is basically 24x. And the derivative of 5y with respect to x is just 0. So here is the electric field in terms of x. And the electric field in terms of y is basically the partial derivative of the potential function with respect to y. So let's deal with x as a constant here. So the derivative of this expression with respect to y is just 5x. And the derivative of this expression is just 0. And here it's just 5. So now we have expressed the electric field in the x and y directions with respect to x and y. So all we need to do is basically test the choices. And the question is asking, where is the electric field equal to 0? So if you see the choice C in my form, the test form I'm solving is basically form 13. In form 13, the choice C is basically x is equal to -1 and y is equal to negative 4.8. So if you plug x to be -1 and plug y to be negative 4.8, then you'll be having 0. And if you plug x here to be -1, then you'll have 0 as well. So the right choice is when x is equal to -1 and when y is equal to negative 4.8, the electric field will be 0 at this coordinate, at these coordinates. Alright guys, so for question number 16, it's another plug and chug question. It's a very straightforward question. So we're given the drift velocity, okay? Meters per second. And we're given the number of electrons per unit volume. Like, imagine we have some sort of wire like this. So this wire, if we zoom into it, like it will look like a cylinder. So the number of electrons that flow in the wire per unit volume is equal to N, or 8.49 times 10 to the 28. So we know the velocity of these electrons, and we know the number of these electrons per unit volume, and we know the resistivity of the material. So we know these three things, and we're asked to find the electric field. So how can we find the electric field? So first, we need to find the current density. And if we find the current density, there is an equation that relates the current density with the electric field. So the current density is basically the number of electrons that passes per unit volume, which is this number over here, times the charge of the electron, which is 1.6 times 10 to the negative 19, which is the fundamental charge, times the drift velocity. The drift velocity is given the problem, and if you multiply these three values together, you'll be getting something like this. So this is the current density. So now, once we have found the current density, we know that the current density is basically equal to the conductivity. Don't confuse conductivity with resistivity. So conductivity is basically the reciprocal of resistivity. Okay? So here, conductivity is how easy the electron can move through some sort of materials. And resistivity, this value over here, which is equal to the reciprocal of conductivity, is how hard or is some sort of representation of the difficulty of going through some sort of material. Okay, so we know that current density from our equation sheet, current density is equal to conductivity times the electric field. And we know that conductivity is just 1 over resistivity, the reciprocal of resistivity. So basically, we could say that current density is basically 1 over resistivity times the electric field, multiply both sides by resistivity. So you get resistivity times the current density is equal to the electric field. So we know current density, we know what resistivity is. Resistivity is given in the problem. So just multiply these two values and you'll be getting the electric field to be 0.18 newtons per coulomb. And that's your answer. Okay guys, for question number 17, it's a conceptual question and it's a reasonable question. It's not easy or hard. So there are a couple of ways you could tackle these questions. So one way you could test the choices. Testing the choices isn't that hard in this case. And alternatively, you could solve it by inspection. So we have 2 sheets of insulating two insulating sheets of charge. And we know that when we have an insulating sheet, the electric field at any point around the insulating sheet is going to be equal to the surface charge density over 2 epsilon naught. Epsilon naught is just a constant and it's equal to 8.85 times 10 to the negative 12. But we're not concerned about this here. Okay, what we care about is we want to express the surface charge density of A and B in terms of sigma. Okay, so I'm going to go over like the inspection sort of solution. So as we can see that the electric field in this area and the electric field in this area are identical. And they are bigger than the electric field inside. What does this mean? It means that inside here in the middle, we have subtracted two values. Some sort of electric field going in this direction, and some sort of electric field going in that direction. And on here, we have added two electric fields. Same on here. It's an addition. Okay. So we need to figure out or think about two values of sigma that if you add them, you get 3 over 2 sigma times sigma over epsilon naught. And if you subtract them, you get sigma over 2 epsilon naught. So if you take A to be 2 sigma, then just apply this equation. Electric field due to A is equal to 2 sigma over 2 epsilon naught. And electric field due to B will be sigma over 2 epsilon naught. So if you add 2 sigma over 2 epsilon naught plus 1 sigma over 2 epsilon naught, you'll be getting 3 sigma over 2 epsilon naught. And if you add this here again, you'll be getting 3 sigma over 2 epsilon naught. And it makes sense that they are both positive, because if you have a positive charge here and positive charge here, both of these sheets are going to repel, like have a double electric field on a test charge on here. So in the middle, this B is going to generate this electric field in this direction on the test charge. It will be pushing on the left, to the left, and for A, it will generate this electric field. So therefore, we are going to subtract these two electric fields, and since A is 2 sigma, then the difference between the two electric fields must be sigma over 2 epsilon naught. Okay, so there is one thing I wanted to add to this here. Since the direction of the electric field in this here, to the right, then that necessarily means that A is the bigger charge. Because if B was 2, let's sort of reverse this. This is wrong, okay? This is not the right answer. But if you make B to be 2 epsilon naught, then the net electric field will be in this direction. This is wrong and this is wrong. Since the electric field in this direction, then A must have the 2 sigma and B must have the 1 sigma. The bigger charge generates the stronger electric field, and the stronger electric field is going to win the subtraction, and the direction of the net electric field must be in the same direction as the stronger electric field. And that is your answer. Alright guys, for question number 18, it's a pretty easy question, given that you know the physics behind the question. Okay, so it says we have 2 insulating spheres. Like this here is not a circle, it's a sphere, okay? And this also is a sphere. These 2 spheres are insulating, which means we can use the equations for the electric field for insulating spheres. But before that, we have to understand that the electric field at this point point P, the net electric field is 0. Okay? And we need to know that the radius, or the distance from here to here, is 0.6. And the distance between point P and the center of the sphere is 0.3. So, okay, so if we have an insulating charged sphere, and we have to find the electric field at any point outside of this sphere, then we could assume, or we could solve the problem as though this sphere is a point charge at the center. And we could just use the equation for the electric field at a point charge, KQR squared. So this here is the equation by which we can calculate the electric field when we have only a point charge. So for this sphere, point P is outside its radius. Since point P is outside the radius, we could solve the problem as though the whole sphere is concentrated in the center, and we use this equation. So the electric field due to this sphere, sphere number 2, is given by this expression, where R is the distance between the center of the sphere and the point we're interested to find the electric field at. And in this case, it's equal to 0.6 plus 0.3, which is 0.9. K is our constant, it's just 9. So K is equal to 9 times 10 to the 9. And Q here is the charge of this sphere, Q. And by the way, this is the value we're trying to solve for, given that the electric field is 0 at point P. Okay, so after we calculate the electric field due to this ball number 2, let's now calculate the electric field to the first ball, or ball 1. So if we have an insulating sphere, and we want to find the electric field at any point inside the sphere, then we use another expression. It's an expression derived from Gauss's law, but we're not actually required to understand the derivation. But at any point inside an insulating sphere, we can find the electric field to be Q over K times the charge of the sphere. This here is the charge of the whole sphere times the radius, the inner radius, or let's say that okay. So let's say that this here is the center of the sphere, and we will want to find the electric field at this point. So Rn is basically the distance between the center and this point, or the point where we want to find the electric field, over R cubed, or the radius of the whole sphere cubed. This here is an expression. Using it, we can find the electric field at any point inside an insulating sphere. So we can see that point P here is inside ball 1, or sphere 1. So we could use this expression. So Rn is basically the distance between the center of ball 1 and point P, which is 0.3. K is our constant. R cubed is the radius of the sphere, the whole sphere cubed. Okay, just solve for this value. This is the value we're trying to solve for. Everything else in this equation is given. This here is 0, and the rest is given. Solve for Q and plug this into a calculator, you'll be getting that the magnitude of the charge Q is equal to 45. And that is your answer. Alright guys, so question number 19 is our second to last question, and it's a conceptual question. It's also a reasonable question. Okay, so in the question it says that initially we had two balls, then we took these two balls and let them touch each other, so to speak, and then separated them back again. And then after separation, how much or how many charge was transferred from any of the ball to the other. And the question is asking in which scenario, so we have three scenarios, okay? In which of these scenarios the greatest charge transfer happened? Okay, so what we're going to do is basically apply our perfect justice system that we have talked about in the previous video. So what we're going to do is take the average. Like add these 6 plus 4 is basically positive 2, and then divide the average by the number of balls. Like so positive 2 over 2 is just positive 1 and positive 1 on each of the balls. And then do this again for this here, the second situation. Okay, so 2e plus 0 over 2. That's going to be your average, and positive 1e over here and positive 1e over there. And here again, take the average, 14 negative 12 over 2. That's going to be equal to 1. So 1 is basically the charge on each of the balls. Okay, so once we take a look at this final stage after we let them touch and then separate them, we can realize that 5 negative electrons have moved from this ball to this ball. Because the only way to make this ball charged from negative 4e to positive 1e is by taking negative 5 electrons. So the amount of charge that is transferred, so charge transfers from the negative ball to the more, okay, let's phrase this like this. The electrons only travel from the less positive ball to the more positive ball. So here is a less positive ball than this one. And in order to turn negative 4e to positive 1e, we have to transfer negative 5 electrons from this ball to this ball. So this here is the amount of charge that was transferred in this process. Over here, we have this ball with a positive 2e charge, and this one is with 0. So the direction of charge transfers is actually from the less positive to the more positive, so it's going to be like this. So there is 1 electron that was transferred from here to here in order to make this positive 1, in order to make this positive 1 as well. So only 1 electron that was transferred compared to here, 5 electrons. So in our final scenario over here, so we have, so here is the less positive and here is the more positive. And in order to turn negative 12 into 1, we have to transfer negative 13 electrons, or 13 electrons from this ball to this ball. So as we can see that situation 3 is the greatest charge transfer, then 1 and then 2, and that is your order, 3, 1, 2. So we're asked to order these in terms of charge transfer with the greatest being first. So this is the right answer. Alright guys, for question number 20, our last question here, we're given some sort of circuit, and we're told that the voltage across the battery of the circuit is 10 volts. Okay, so this is 10. And there is 2 capacitors connected in series. One is for 6 microfarad and the other 6 microfarad as well. So then we're told that the distance between the plates of the second capacitor is reduced to 1/2 the original distance. And we already know that there is an equation that relates the distance with the capacitance. So if we divide D here, which is the separation between the 2 plates, by 2, this is equivalent to saying that we're going to multiply the whole capacitance expression by 2. So in other words, if you planned out half the distance between the two plates, you're going to double the capacitance. Okay, so C2 is now after, or C2 prime is the capacitance after we reduce the distance, is equal to 2 times C2. Okay, and we already know that C2 here is 6. So C2 prime is equal to 2 times 6 is equal to 12. So the capacitance is now equal to 12 microfarads. So we have two capacitors, one is 6 microfarads and the other is 12 microfarads, connected to a battery that is 10 volts. So the question is asking what is the charge stored in the equivalent capacitor. So what we're going to do is basically add these two. Because these two are in series, we're going to use this equation. We just plug numbers in, like C1 is equal to 6, C2 prime is equal to 12. Plug this here into your calculator, you're getting 4. And we already know that the circuit is going to look something like this after we do the addition, 10 volts. So the voltage across this equivalent capacitor is going to be 10. And we already calculated the capacitance of the capacitor. So just multiply the voltage times the capacitance. Voltage is 10, capacitance is 4. And I'll be getting 40 microcoulombs. And that should be the right answer. So by this question, we conclude the second major exam. And I wish you guys good luck in your final, which will be in a couple of weeks from now. So if you have any questions or require assistance, just feel free to email me. I'll be posting my email in the description below. And feel free to comment constructively on any of my videos. I'll be happy to read your constructive suggestions. Thank you.